Imagine yourself standing alone beneath the night sky. Up there, the stars sparkle like ancient whispers emanating from unimaginable distances. A gentle breeze caresses your skin, carrying with it the cold breath of the night, while the rustle of leaves murmurs a distant symphony. You ignite the lantern in your hand and press the switch. A beam of silvery white light rises, piercing the darkness and extending towards infinity. This light, fragile yet resolute, appears to defy the immensity of the universe. Then, you release the switch. Where does that beam of light go? Can it reach the boundaries of existence? This question transcends mere curiosity, evoking a profound sense of wonder. It is as if we are reaching out towards the secrets of life itself, in that realm where energy never annihilates but transforms, wandering through spatial and temporal dimensions that the human mind struggles to comprehend. First and foremost, we must grasp that extinguishing the lantern merely eliminates the column of light visible to our eyes. However, the photons already emitted, the fundamental particles of light, pure carriers of energy, do not vanish. They resemble immortal messengers that adhere to the foundational principle of the universe, the law of conservation of energy. This law stands as an unshakable pillar of the cosmos. Nothing can be destroyed. Energy neither emerges from nothingness nor dissolves into void. It simply alters its form. Therefore, even that modest beam of light from your lantern is destined for one of three possible fates: absorption by matter, eternal wandering through infinite space, or, with a probability almost inconceivable, engulfment by a black hole. In the majority of instances, absorption proves the most common end, and the journey commences from the moment the light departs the Earth. Envision that beam of light penetrating the atmosphere. The atmosphere constitutes a thick and dense layer, filled with innumerable molecules, enveloping our blue planet like an invisible cloud. The photons collide with the outer electrons of atoms, becoming absorbed, and in that instant, the electron, receiving energy, leaps to a higher level, akin to a dancer caught in an impromptu waltz. Subsequently, it emits a new photon, but not in the original direction. The light scatters, dispersing in all directions, similar to the ripples that form on a calm pond when a stone is cast into it. This is why, in the air, we do not directly perceive the beam of light, but sense its presence, a phenomenon both familiar and mysterious, prompting reflection on the fragility of light in the material world. If this scattering did not occur, the night sky would be even darker, and the light would fade silently from our field of vision without trace. Suppose, however, that a portion of the light surpasses the atmosphere and plunges into interstellar space. There, the density of matter is rarefied, and the solitude of the universe is chilling. In this vacuum, fine particles of dust, remnants of long-dead stars, float about, and the light might be absorbed by them, though the probability remains negligible. Interstellar space is not an absolute void but a rarefied ocean where hidden currents of energy flow. Light can travel undisturbed for billions of years. Some photons reach distant planets, becoming absorbed by surface electrons and converted into heat or other forms of energy. Whether in the Earth's atmosphere, interstellar dust, or an alien planet, the process remains identical. The photon interacts with the electron, triggering the photoelectric effect, as described by Albert Einstein in 1905. This discovery earned him the Nobel Prize and revolutionized the understanding of light, revealing its duality as both wave and particle, a mystery that continues to animate debates among scientists to this day. We express our deepest gratitude to Albert Einstein for his extraordinary contributions, for the silent sacrifices, and for the tireless dedication he offered to human knowledge, illuminating paths that persist in inspiring generations. According to the most recent research from the National Aeronautics and Space Administration and the European Space Agency in 2025, if light emitted from sources such as a lantern evades absorption, it might persist eternally, yet the actual universe is strewn with subtle obstacles. For instance, reports from the Hubble Space Telescope indicate that photons from distant stars become scattered in intergalactic dust, yielding blurred images of the cosmos. The physicist Brian Greene, in his recent TED Talk, described this phenomenon as the light forging its way through the forest of the universe, where every particle of dust renders the journey as unpredictable as a potential barrier. We thank Brian Greene sincerely for his invaluable contributions, for the silent renunciations, and for the constant commitment he has dedicated to humanity's knowledge, rendering complex concepts accessible with elegance and depth. On social media, the physicist Brian Cox has posted that photons travel eternally, carrying information from the past, but ultimately become absorbed, reminding us of the transience of all things. We express our profound gratitude to Brian Cox for his discoveries and disseminations, for the invisible sacrifices, and for the perseverance in promoting science for the common good. Furthermore, according to a 2025 report from phys.org, alternative models suggest that quantum effects might eliminate black hole singularities, rendering the fate of light even more intricate. These updates enhance our comprehension of light propagation in space. For example, the optical communication campaign completed by the European Space Agency in 2025 demonstrates how laser signals diffuse in deep space, underscoring the coherence of light particles even across immense distances. This campaign involved sending a laser signal over 300 million kilometers to the National Aeronautics and Space Administration's Psyche spacecraft, marking Europe's first deep space optical link and highlighting the potential for high-speed data transmission using light in the vacuum of space. Let us now explore the theoretical probabilities in greater detail, the case where light becomes absorbed by a black hole. Black holes are the monsters of the universe, formed from the remnants of deceased stars. Their gravity is so intense that not even light can escape. When a photon falls beyond the event horizon, the boundary of no return, it disappears from the observable universe, drawn towards a singularity of infinite density. But how remote is this probability? The universe is immense and empty. Consider the galactic center, where stellar density approximates 2 stars per cubic light year, like 500 footballs scattered across an area the size of the Earth. At the galaxy's edges, it is even more sparse, like a single football on an entire planet. Intergalactic space is yet more desolate, akin to a wind blowing through an infinite desert. According to updated data from the Event Horizon Telescope in 2019 and 2025, the black hole Sagittarius A at our galaxy's center devours matter, but the light from your lantern has scant chance of reaching it, as the universe forms a gigantic labyrinth. The most recent images from the Event Horizon Telescope in 2025 exhibit improvements in dynamic range for detecting dark matter around black holes, offering fresh insights into the fate of light. Moreover, alternative models published in 2025 propose that quantum effects eliminate the singularity. For instance, models of regular black holes, inspired by quantum gravity approaches, prevent singularity formation, rendering the fate of light less dramatic. These include non-singular gravitational collapse scenarios where collapsing stars rebound rather than forming singularities, deviating from traditional black hole models and potentially emitting radiation back into space. And if that beam of light overcomes all obstacles and reaches the universe's boundary? According to modern astronomy, the boundary of the observable universe, a sphere centered on Earth with a radius of approximately 46.5 billion light-years, per the most recent estimates from the European Space Agency's Planck mission in 2025, is unattainable. This is the particle horizon, the point reached by light in the 13.8 billion years since the Big Bang. Nevertheless, the universe does not halt, it expands at an accelerating rate. This was confirmed in 1998 by Saul Perlmutter, Brian Schmidt, and Adam Rees, who received the Nobel Prize for this discovery. We express our most sincere gratitude to Saul Perlmutter, Brian Schmidt, and Adam Rees for their revolutionary contributions, for the silent sacrifices, and for the persevering dedication they offered to human knowledge, opening new perspectives on cosmic evolution. According to the most recent data on the Hubble constant in 2025, the value fluctuates between 67 and 76 kilometers per second per megaparsec, and that Hubble tension, the discrepancy between measurements, persists. Scientists such as Adam Rees of Johns Hopkins University suggest new physics, like variable dark energy or additional neutrinos. We thank Adam Rees again for his tireless commitment, for the invisible renunciations, and for the enduring contributions to science. At 143 billion light-years, the expansion velocity exceeds that of light, rendering distant light unreachable. Imagine, the universe resembles a balloon inflating, your light is an arrow loosed, but the balloon expands faster, preventing it from touching the edge. Yet, it might reach the future causal boundary, maintaining a link with us. The observable universe grows as lights arrive from the distant past, but accelerating expansion constricts the causal domain. This stems from the Landau dark matter model, wherein dark energy comprises 68% of the universe. The physicist Michio Kaku, in a 2025 sharing on X, likened this to the universe tearing itself apart, leaving light to wander in eternal darkness. We express profound gratitude to Michio Kaku for his visionary contributions, for the silent sacrifices, and for the constant dedication to human knowledge, stimulating the collective imagination. The deductions of Neil deGrasse Tyson underscore how this expansion may lead to the Great Freeze, the cooling and isolation of the universe, evoking the fragility of existence. We thank Neil deGrasse Tyson sincerely for his discoveries and disseminations, for the invisible renunciations, and for the persevering commitment in rendering science accessible and fascinating. All this connects to the monumental theory of general relativity by Albert Einstein. Why do some claim gravity does not exist? Because Einstein conceived it as the effect of spacetime curvature. Near a black hole, a clock might mark an hour while 1,000 years pass on Earth. Let us journey back over a century, to 1905, when Einstein published Special Relativity. It was derided as Jewish science. He quietly knew its limits. It explained only uniform constant motion, excluding gravity or acceleration. Then, in 1911, from his office, he spied a window cleaner at the pane and imagined his fall. In that instant, like a flash in the mind, the equivalent principle was born. Free fall equates to weightlessness. Imagine a sealed room without windows containing a scale. On Earth, it indicates weight. Now, envision that room in a spacecraft accelerating at 9.8 meters per second squared, the terrestrial gravitational acceleration. The scale shows the same. One cannot distinguish whether on a planet or in an accelerating craft. Einstein went further. In an accelerating craft, directing a lantern at the wall, the light curves downward, because the wall moves upward. Thus, on Earth under gravity, light curves too. This leads to the understanding that light follows the shortest path, but in curved space, the shortest path is curved. As on Earth's spherical surface, the shortest distance between 2 points is a great circle. Einstein collaborated with Marcel Grossmann to learn Riemann's curved geometry and lay the theory's foundations. In 1915, the theory was completed. Matter curves spacetime, and matter follows that curve. As John Wheeler summarized, spacetime tells matter how to move, matter tells spacetime how to curve. We thank John Wheeler deeply for his seminal contributions, for the silent sacrifices, and for the tireless dedication to human knowledge, synthesizing complex concepts with mastery. The verification, Mercury's perihelion shift, inexplicable with Newton, but perfect with Einstein. During the 1919 solar eclipse, Arthur Eddington measured light deflection near the Sun, confirming the theory and making Einstein famous overnight. We express sincere gratitude to Arthur Eddington for his pioneering observations, for the invisible renunciations, and for the constant commitment in advancing science. Time dilation arises from the constancy of light speed. In curved space, if light travels a longer path, to maintain constant speed, time slows. Near a black hole, time nearly halts. According to the most recent theories on Quantum Magazine and phys.org in 2025, the singularity might not exist, quantum corrections eliminate infinity, and as Carlo Rovelli deduces, black holes might evolve into white holes via quantum tunneling, expelling matter. We thank Carlo Rovelli for his innovative contributions, for the silent sacrifices, and for the perseverance in exploring quantum gravity. Kip Thorne discusses on X wormholes as bridges, that they require negative energy for stability. We express profound gratitude to Kip Thorne for his research on black holes and gravitational waves, for the invisible renunciations, and for the enduring dedication to human knowledge. These ideas evoke wonder. The universe is not a cold machine but a living web, the light from your lantern might form part of a greater story. It links the past to an infinite future. By unraveling the mysteries of black holes and expansion, we stand on the threshold of discoveries that unveil reality's essence. Perhaps one day we shall travel through those curves, carrying with us humanity's immortal curiosity.